Recorded is rolling. It is Wednesday, March 18th. So yesterday we were close to the end of circular motion, so I've got a couple more examples for you guys. I'm going to universal gravitation. Of course, you can put together circular motion and gravitation to make orbits. And so this tomorrow, you guys get the quiz on what we've been covering this week. All your papers have been returned to your folder, so anything you turned in at this point, if there's something you haven't turned in, like a recent lab or something, then make sure you get that in too, because we're real close to spring break. Get real close. All right, so yesterday, you guys saw this, and then the bell was ringing. So do you guys remember the free body diagram? Let's do the car at the top of the hill. Now notice it is in motion. If it was parked, there'd be a weight down, normal force up, and they would balance out, right? But if it's in motion, now those forces are different. Guys, would this car be in equilibrium? No. Which force is bigger?
The weight.
Yeah. Are you guys saying the weight down is bigger? Right. Well, what would it feel like inside the car? Would you feel a little bit heavy or a little bit light? A little bit light. Yeah, which means you guys are exactly correct. Yeah, the normal force is less than the weight. Yeah. What you perceive as your apparent weight is something like the normal force, like if you're sitting on a scale. Right. Well, what about if you're zooming through this valley? Now what? Yeah, the actual Earth's gravity pull on the car, that didn't change. Okay. But the normal force on the road definitely did. Okay. Right, so you guys go with that. All right. Ooh. So near the beginning of this, you guys did this experiment with the PVC pipe and the plated canisters and the weights, and you were swinging this around. Right. And we were assuming that the circle was exactly flat and the string was horizontal. But if you think about it, really, there was a really shallow cone, right? And actually, if you're swinging this mass around kind of slowly, it was more pronounced cone, like this conical pendulum. This would definitely create a cone shape, wouldn't it? Right? Hence conical, right? And so, see what can you guys come up with this? I've definitely seen AP ask questions about this before. Right? So, what's one force acting on this mass right here? Yeah, it's weight straight down, mg. What's another force? Yeah, the tension in the string, which is now definitely at some angle, isn't it? All right. And notice I'm giving you the angle relative to the vertical. If you run to the scenario in the AP exam, which you well could, they'll probably give you that angle from the vertical. They might do it from the horizontal. So just be ready for that. Because guys, suppose this angle, I'm just going to make something up. Okay, suppose this angle is 40 degrees. I'm just making something up. Because if this is 40 degrees, what is this angle right here? 50, right? Because it would have to be complementary. It has to add up to 90. Right? Okay, so just in case so. Okay. Guys, are there any other significant forces on that object? Yeah, you're the announcing today. Yeah. No, that's it. That's all the forces. There's only two forces. Right? Now it is in motion, but the direction of its velocity, there doesn't have to be a force. It's just going. Right? Inertia, momentum, whatever. Let's see what's next on this. All right, guys, what is the net force? What's the direction of the net force on that object?
Plus.
Are you guys saying towards the center of the circle that's dashed outlined in green? Yeah, I think so. And in general, couldn't you always get net force by doing the sum of the forces there, like add vectors tip to tail? And if you do that, you can add either one tip to tail with the other. No matter how you do it, you'll get the net force. Yeah, it's directed straight towards the center of that circle. Do you see that too? You guys are thinking in 3D. Okay. What's next here? Oh, okay, guys, let's come up with an equation for the forces in the vertical direction. So if I introduce a Cartesian system and I have a y-axis, okay, can you? There's a formula that's going to pop up right here, the top of this box. Can you guys come up with a formula to talk about the force or force components in the y direction? What do the forces sum to in the y direction? Yeah, it has to be zero because that object's definitely not moving up or down at all. Okay. Now, horizontally, it's a different story, but vertically, yeah, vertically has to sum to zero. Okay. Can you guys come up with an equation or sum to zero? Okay. Take a quick trip around the room. See if you guys were able to come up with the expression. Okay. So we made a free body diagram. You'll have to refer to that. All right. Yeah, Austin got it. Lily got it. Yeah. Okay. I think Logan got it. Okay. Okay. Yes. Some of you guys are getting this. All right, so much class time. Get move this along here. Right, so what you guys are saying is if you break this tension into components, what component of the tension is pulling straight up? Ft times what? Cosine theta. You see, cosine theta would be adjacent to the theta. That's what cosine is. Okay? And that would have to balance out with the weight. So Ft cosine theta up and the mg down have to zero out. Is that true? So I would write that right there, which a few of you guys got. Okay? And everybody has to know that by the AP exam. Okay? So get a good look at that, digest that, say, ooh, either I got that or I definitely should have gotten that. Okay? Now let's go horizontal. You guys ready for horizontal? Because that's vertical. That's all in the y-axis, just up and down, parallel to gravity. Okay. Now let's do horizontal. Now horizontal, do the forces still sum to zero in the horizontal? Definitely not, because it's on a curved path, on this curved horizontal path. Can you guys think what would be a valid equation in the horizontal that goes right here? Write something right there. What's a valid equation in the horizontal? Yeah, what is pulling this into a circle? Ooh, what did I hear about a sine? You said sine. All right, Victor's saying sine. So you said Ft times sine? Yeah. Okay, so take this tension, multiply by sine theta. Right? No, that actually looks like this brown net force right here, right? Right. Okay. So the tension force times sine theta could represent the net force, couldn't it? Right. Further, you may have actually written a little differently. Because maybe you didn't write net force. Maybe, that's actually what this is down here. Guys, what is the net force? What's the little expression for it? It's a fraction. What over what? mv squared over r. Remember that? Yeah. Yeah, when you guys originally did this, you were assuming a flat circle, so you said, well, the tension is, you said the tension is mv squared over r. Now we're getting a little more nuanced. We're saying, well, yeah, if it's something more conical looking, it's really the sine component. All right. You guys can navigate that? Conical pendulum? All right, next example we're going to do is actually mathematically very, very similar. You guys ready for the next slide? And that's a car going around a curve. Car around a curve. Okay? Now, before we jump into the diagram and the math of it, what's going to help you out is imagine your experience inside the car. As you're going around that curve, do you feel a little bit light or a little bit heavy? A little bit heavy, which tells you something about how the vectors should compare to each other. And so let's put some vectors on this. What's one force on this car? Okay, so I'm hearing weight and a normal force. Okay, which direction does the Earth pull on the car? Straight down. There's your mg or F sub g, either way. Okay. And which direction does the normal force point? Yeah, perpendicular surface. That's what normal is. Okay. Now, how long should you draw the normal force for this particular scenario? Is it longer or shorter than the weight?
Longer.
Who says longer? Who says longer? Yeah, I agree with you. I think it should be longer. Right? Reason being, here, if you break this into components, the vertical component of this normal force has to uphold the weight, has to balance out the weight, and the horizontal component, I think, has to do something with the car turning. Okay, you guys, that is different than a block sliding down an incline. As a block sliding down the incline, the normal force was shorter in magnitude, or less than smaller magnitude. Right? But a car zooming around, it's the opposite case. Okay, look at that. Okay, so I got this component labeled mg. Isn't this normal force times cosine theta? Is that true? That might be helpful here pretty soon. Normal force times cosine theta is mg, right? But what about this bit right here? What could you say about this? Yeah, is that normal force times sine theta? Right. And furthermore, that's equal to what over what?
mv squared over r.
mv squared over r. There you go. Great. So this bit is the net force, and that's mv squared over r. And you guys are right, that is normal force times sine theta. Right? Well, guys, let's put these together. If this is normal force sine theta, and this bit over here is normal force cosine theta, guys, sine theta and cosine theta, that something about the two legs of the triangle. You could push that all together and make what third trigonometry relationship? Tangent. So there's about to be a tangent popping up here. Right? So if you start with this leg, which is mg, you guys see mg right here? I'm kind of walking you guys through this one. Right? Mg. And you multiply by tan theta, what does that give you? Yeah, it gives you this leg right here, which is mv squared over r. Okay. So based on what I just said verbally, come up with an expression for what I just said. Right. And I'll say it again. Okay. You guys were also leading along to step by step. Right. If you start with this leg right here, mg, and you were to multiply that by tangent of theta, that tells you something about this opposite leg, which is labeled, well, all this right here. Right. So can you write that down mathematically? All right, what'd you guys come up with? Boom, mg tan theta is mb squared on r. Okay. Okay. All right, so doing one step at a time. I think I only have one animation piece left here, and that's the equation that goes in this box, and it's to rearrange it. Okay. I mean, I guess there's a bunch of variables. There's different ways you could rearrange this. Okay. So the scenario here, what you guys are thinking, like, take your best guess what goes in that box. Right. The scenario here could be maybe you're maybe you're an engineer one day and you're designing roads, and the road's going to go around a curve, and maybe there's an expected speed limit. You're coming off the interstate, so okay, I got to go going like 45 miles an hour because they can't go any. Right. And okay, there's only so much land to work with, so there has to be a particular radius of curvature. So I'm locked into that. I have to figure out how much I need to bank the road. What is this theta right here? That could be a reasonable thing you'd have to calculate as an engineer, can it be? Okay, how much you have to bank the road so that the car's not flying off the road? All right, so this will get a little bit closer. Here, which variable did you guys cancel out? Mass of the car. Right, so if it's a little motorcycle or if it's a big old semi truck, do they both need the same embankment? Yeah. So the mass of the vehicle doesn't matter. Right. There's one way you could. There's probably a few different things you could have written there. Right, that's one thing. Yeah. The most important thing about that one is the process, the thought process. Can you do all the trigonometry? You can see all these relationships. Yeah, that's how you solve for theta. Yeah, take the inverse tan or arctan. Yeah. Solve for theta. All right, you guys good there? Good there? All right, so that was a couple extra slides from yesterday. All right, you guys ready for gravitation? Gravitation. All right, so historically, I think a good place to start is Kepler's laws. I don't know if this is going to show up on the AP exam, but it's maybe good to know these anyway. Does anybody remember these? What's Kepler's first law?
There's like two things, and it's like this, and this like planet here.
Yeah. All right.
Yeah, that one.
Yeah. So planets actually move in ellipses around their parent stars. Not actually circles, although they're really close to circles. A lot of times we approximate them with circles, but they're actually slight ellipses. Okay? And then if you get more extreme objects like comets, they're like definitely ellipses, like obviously ellipses. Okay? Does anybody remember second law?
Is this like the one that's tons of universal gravitation or something?
Right. Oh yeah. It's about triangles. It's triangle wedges. Right. Yeah. I think Justice is on this one. Right. So here, I'll lead into this. All right. Here's actually a question you might ask. Guys, where's the planet moving a little faster? When it's far away from the star or close to the star? Close to the star is moving a little faster. I've seen them ask energy questions about that. There's more kinetic energy over here and more potential energy over here. Although the total energy stays the same, doesn't it? Total mechanical energy. Okay. All right. So a little faster on the close side, a little slower on the far side.
Triangles.
But yeah, all right. There's the triangles Justin was talking about. But if you make these wedges, these triangle-looking wedges, it's all these could have equal areas and equal times. So maybe it takes like 30 days to go from here to here, and 30 days to go from here to here, and 30 days from here to here. Those would all be equal size wedges and equal times. Right. So right. And then third law, this is the one that eventually bridges to Newton. Who came later historically. This says if you look at the amount of time it takes the planet to go around, like so for Earth, this could be 365 days. Right? And you compare what is its average distance from the star. Here's where we're approximating circular orbits a little bit. Okay? We have a square cube relationship. Right? Now, if you bring in Isaac Newton and you do all the math, it actually also confirms that. Right? So here's the Newtonian update with the universal gravitation. And guys, which end is this? Is this the mass of the planet or the sun? This is the sun. This is the sun. Yeah. Which is like 99% of the mass of the solar system. All right, so you guys good? Go here. Inverse square law. All right, so here's a good visual. Right, if your eyes say like 1 foot away from this candle, your pupils picking up all the light. If you back up twice as far away, how much light do you catch? a quarter. 3 times far away, you catch how much light? A ninth for the same like size pupil, right? And so we got an inverse square law, right? So this is the consequence of living in a 3-dimensional universe. There's your back way. Right, so that's a good lead into Now this one is on your AP formula page, but do you have it memorized?
No.
I think it's another one that's good to know. It's looks like it's about a third of the way down your formula page. I'll go point it up. Okay. Go ahead, write it down. See if you remember it. Did you guys write this one right here?
Oh, yeah, no.
You guys remember that?
Oh,
Remember that? Yeah, it's about a third of the way down on the page.
I'm not squaring wrong, but there's a square.
Alright. So you guys came up with that?
Oh, I put that right.
Yeah. Right. So the force of the Earth pulling on the moon or moon pulling on the Earth, right? We got here's the mass of the Earth, the mass of the moon. Divide by the distance between them squared. You guys, distance, is that surface to surface or center to center? Center to center. Right? And then universal gravity constant. So the Earth pulls on the moon. The moon also pulls on the Earth, right? Okay. You guys, which of these forces is actually bigger? The Earth pulling on the moon or moon pulling on the Earth? The same. The same. Yeah, that would be Newton's third law, wouldn't it? Right. And then there's your universal gravity constant, which is actually also listed on the AP page, but on the other side. Here, I'll point it out to you guys real fast. Okay. So here, normally we're looking on this side, but if you flip the page over, they give you some values, including this one right here. Okay. So if you need that, it's there for you guys. All right, you guys good with that? All right, back in 1880, here's one of the first ways this gravity constant was originally found. He set up this balance and did this math and saw it. Okay, so there's a little fun side. Here's the Earth and the Moon to size and distances to scale. Okay, that's fun. If you back way up in space and looked at the system, that's what it would look like. I could see some AP questions about this. Suppose you have a planet with some mass and some radius. Okay, and let's really simplify this. Let's assume that it's uniform density all the way through, which might be true for some small asteroids. Although it's not exactly true for planets, but let's make believe. Okay? Simplification. We do lots of simplifications in here. All right. Can you guys come up with an expression for the density of the planet, like the density of Earth dirt in terms of its mass and its radius? Can you guys do that? And what about gravity field? Go ahead. What do you think goes in those two boxes right there? That yellow box and that green box.
I don't remember.
Take your best guess. What is density? It's a ratio of what over what? Mass over volume?
Yeah.
Right? Huh. And what shape is the Earth? Starts with a S. The sphere? You guys know the volume of the sphere? Is that on your...
It should be. I think it is.
Yeah, that is on the AP equations. Here, I'll flip back over again. I think this is a good one to know. I mean, it's one of these things that keeps coming up. It's near the bottom here. It's there it is. Volume of a sphere is 4/3 pi r cubed. And here's the surface area for that matter. Yeah, I think that's a pretty good one to know. Yeah, space in your brain, like, I need to memorize one more fact today. There you go. All right, what do you guys come up with for this fraction right here? How about that? Yeah, you do that. A few different ways to write that. Okay. How about gravity field? What do you guys write for gravity field?
9.8.
Well, okay, for Earth that would be true. Right? What about a different planet? How about in general?
Yeah. Oh.
Yeah, guys, it looks like universal gravitation, except you divide by the mass of whatever's at the surface. Okay, like how about all of us in here? All of us in here have different masses, but don't we all experience the same gravity field? Yeah. Right, which okay. Right, so I care about the mass of the Earth to get the gravity field.
Okay.
All right, and really that's a setup for this one. Right here, I've seen AP ask questions like this before. Is what if you have a planet that's so many times Earth's mass and so many times Earth's radius, and there's variations on this question. Right? Can you tell me what the density of this planet's dirt would be, again, on average, right? Or what the gravity field would be at the surface of planet X? Got some planet X out there, shiny gold planet. Ooh. I'm telling you that it's sometimes Earth's mass and 3 times Earth's radius. Can you figure out what's the density of planet X's dirt compared to Earth? Okay. Here's the density of Earth dirt. Here's the density of planet X. Okay. And what is the gravity field at the surface compared to Earth? So you guys know on Earth we're like approximately 10 meters per second squared running around, right? But on this planet, would you feel kind of light or kind of heavy? Right? Or how many times Earth's gravity would that be?
Yeah, that's.
Go ahead, do the math there. Give you guys a minute to do that math.
I mean, it's just a lot of kids.
Do that math. I think you should fully expect to see some version of this question on the AP exam coming up in a few weeks. What goes in those blank spaces up there? And what's the answer to both those questions? What's the density of that planet? What's the gravity field on that planet? Sometimes Earth's mass, 3 times Earth's radius. All right, here, I'll walk you guys through it. All right, so here's Earth's setup right here. Now you guys know density in general is mass per volume. Volume is 4/3 pi r cubed. Right? Hey guys, the 4/3 and the pi, that's going to end up canceling out by the end. But it is important that you're cubing the radius. So up here for planet X, could I say 7 times mass Earth up here in the numerator of the numerator? Right? And then for radius, I have 3 times, but that's being cubed. Guys, what is 3 cubed? 27? 3 times 3 times 3? 27? Right? And everything else is going to cancel because this is all in terms of Earth values. So mass Earth, cancel radius Earth, cancel 4/3 pi, cancel. Okay. I think you're going to end up with 7/27. I think that should be the answer, shouldn't it? 7/27? Let's see, is that... yeah, there it is. 7/27. Okay? Right, okay? Right. Which is approximately a quarter. So maybe this planet's a giant puff planet made out of styrofoam. Now, what about you're running around on the surface? Now, I do see this planet is way more massive than Earth, but also has a larger radius, and we already figured out that it's not very dense. So, would you feel heavy or would you feel light? Well, we're running into this ambiguous scenario. Okay? So let's run the math here. So here I have an Earth gravity field, gm over r squared for Earth. Okay? Now we've got 7 times the mass of Earth, so there's going to be a multiple of 7 up here, right? 7. And down here, I got 3, but what's happening to the 3? It's being what? Squared. Guys, what's 3 squared? 9. And so what's the overall fraction? 7/9. And everything else cancels, doesn't it? Boom. Boom. 7/9. Yeah. 7/9. Okay, that's pretty close to 1, so it's a little less. So would you feel a little bit light or a little bit heavy? Yeah, a little bit light. Say, ooh, not by much, but a little bit. Probably notice it. Okay, you guys gonna do that calculation? And of course, you guys know I uploaded this file, but a couple weeks ago, and uploaded this video later. So you guys have all that. Oh, orbital speed. Deriving from scratch. Go. This keeps coming up over and over. This is probably the 4th, 5th time. How do you guys do this? Derive orbital speed from scratch. Wait. You can derive orbital speed from scratch. Starting from, of course, the equations on the AP page. You're allowed to know those.
Second. I think it goes that way. And then the first one to 4 is. We'll get it eventually. Well, MA and B squared over R. And B squared over R. And then
No, I don't have a very good visual for this slide, so yeah, I'll be guys out with the picture.
mass don't cancel because the mass is.
Alright, so here's your planet. Here's the satellite. So the satellite is just above the atmosphere, so that
The universal
this R is pretty close to the planet anyway. It's go around.
Yeah.
And there's some beam here to keep it in orbit. This has some mass. This has a different mass. Alright, let's do a free body diagram on this satellite. Guys, what's one force acting on the satellite? Yeah, it's on the weight. Now, I'm not gonna Okay, I'm gonna write this way. I'll call it F sub G because I'm gonna think in terms of universal gravity. Okay, just think about it a little bit. Is there any other force on the satellite? No, that's it. That's the only force. Is that satellite in static equilibrium? Not at all, because there's a net force on it. It's always falling. It's just falling around the curvature of the Earth. It's falling. It's perpetually falling. So that'll start you out. Okay. Now from that, you can get this V.
That mean that mass is also.
All right, what'd you guys come up with? Huh? Here, show hands. Who thinks they know the answer? Who got the whole answer? Ooh. Okay, all right, let's go step by step. What'd you guys just write? It's the very first step. What is equal to what? GMM over R squared. There's your universal gravity. That's equal to that force is acting as the what force? The centripetal. Net and centripetal. Yeah. Sure, same thing. Yeah. Okay, centripetal. Okay. And what's the formula for centripetal force? mv squared over r. Oh, okay. Okay, so I guess that's the next line. Okay. But when you say mv squared over r, that m, is that the mass of the satellite or the mass of the planet? Satellite. Yeah. Right. So there's the mass of the satellite. Right. Here's the mass of the planet is the big M. Right. Big M's the mass of the planet. Little M's the mass of the satellite. Okay. Are you guys okay after that step?
Yeah.
So the gravitational force is acting as the centripetal force. That leads to that pair of equations, or that equation. Can you guys finish that off with the algebra? Finish with the algebra. We solve for V. Okay. Now, notice this is actually for a circular orbit. Right? So realistically, you might want to go a little faster. All right. What do you guys come up with? Yeah, root GM over R. Yeah. Also a good one to know, and make sure you can derive that from scratch. Make sure make sure you can derive that from scratch. All right, guys, good. All right, orbital paths. All right, so all right, let's start with the circular path. So you guys see a satellite right here, and here's R. Okay, so that circular path. So if it's going root GM over R, it'll stay on a circular path, which, yeah, not super stable because if it slows down for whatever reason, it'll eventually spiral and crash. Okay. So realistically, you want some kind of elliptical orbit, just like the planets are doing. Okay. So you have to speed it up a little bit, wouldn't you? You have to. Oh, okay, I forgot about that. Okay, guys. Something that's reaches. Does this look like escape speed? Do you remember escape speed? Okay. We were able to derive that after we got to energy and conservation of energy. So we haven't actually quite hit that by this point in the review. Okay. But anything that's elliptical is going between those two values. Okay, that'll be on this elliptical path. Okay. All right. So here, synopsis here. What's the gravity field of a planet again? Well, what about Mars? What over what? There's a fraction.
R squared.
GM over R squared. Okay. Universal gravity constant, mass of the planet, we raise the planet squared. Okay. What's the orbital speed? Root GM over R. Right. For a circular orbit, so you have to go at least that fast to stay in orbit. Right. And then if you want to escape, you have to speed up to how fast? Yeah, it turns out if you just slip a 2 in there. Right. Now that 2 is underneath the radical also, so really couldn't this be the square root of 2 times the orbital speed? Like for example, if I told you the orbital speed around Earth is like 7,900 meters per second, you could multiply that by the square root of 2 to figure out what's the necessary escape speed. That's like a minimum value. All right. Ooh. What about this? Here's a scenario. You're watching this moon go around this planet. Right, maybe you're Galileo and you're watching one of the big moons go around Jupiter. Now, if you can get this distance r through the telescope, estimate that.
Why do we do that?
And also you can time it. How much time does it take the moon to go around? Do you think there's enough information lying around? You can calculate the mass of the planet. Okay. Now, you can either start with orbital speed. Okay, there's a little bit of math, or you can start from Kepler's third law, like that Newtonianized version. Okay. Now, I did help you guys out on the orbital speed side a little bit, because orbital speed, guys, could orbital speed be total distance over total time? And what's the distance around a circle? 2 pi r, isn't it? Again, we're fudging this a little bit because it's really more elliptical, but pretty close to circle. Right. Right? And then this t could represent the time period to go around, like how much time. Right? Yes, suppose it takes so many days to go around. I'm just gonna make some up, like 19 days. If it takes 19 days to go around, do you want to put 19? Is that what you want to plug in for t? Why not? It has to be in seconds. Has to be. Can you convert 19 days into seconds? Yeah, which would be like many seconds. Okay, so it's gonna be a big number. All right. Okay, so go ahead and do the algebra. Let's do a little algebra here. Take this. All right. Okay, so you guys derived orbital speed a couple slides ago. Right. I helped you guys out here saying, oh, by the way, orbital speed is 2 pi r over t. Right. Can you guys finish off the algebra? Can you guys take this expression and rearrange it and solve for the mass of the planet? This big M right here. Go ahead and do that. Algebra. Some algebra. Okay, who gets this correct? You're watching the moon go around, it's pretty circular. Or maybe send a satellite to some planet and get a satellite going around a circular orbit. From this we can get the mass of the planet. Do some algebra here.
What do you get?
All right, so if I was solving this, I think the first thing I would do is square both sides. Yeah. Like I'm trying to unbury this m, so I got to square everything. Then I would cross multiply the r, and then I would divide down the capital G.
Oh,
right?
it is that.
Hey guys, those are 3 steps. I'll say those 3 steps again. First step is square both sides to get rid of this root. So now everything's squared on the left side.
Switch to that.
Then cross multiply the r, then divide down the g. Wouldn't that be it? 1, 2, 3.
That's how Kepler did it.
All right, show of hands. How many guys had that on your paper? Yeah, all right. Some of you guys do. Some of you guys do. Right. That was all. That was just a few algebra steps. They're there. You guys got to be able to do that algebra. Do that algebra. Be able to go from there to there.
All of algebra was cheating. Bro, we're doing factor. Okay. For the 85th time. Do you know any factor? Yes.
Ooh, eggshell planet. Right. No, this is a good I guess textbook scenario, but it does help explain other questions too. Right. And so let's say you're trooping around the galaxy, you find I found this eggshell planet. You're walking around. Okay. Hey guys, if it's an eggshell planet, can you walk around on the surface and the collective mass of this eggshell pulls you towards the center?
Sure.
Yeah, you can walk around on the surface. That's okay. Okay. But if you dig a hole and you step inside, now you're this point mass right here. Okay. Let's say you're floating around right here. Are you pulled more to the left or more to the right?
Same.
Same? You're saying same? All right. Let's take a look here. Because you can go something about GMM over R squared, right? Right. Now here, this eggshell piece right here has some, maybe it's like a meter thick. Is that okay? It could be a meter thick all the way around. It's an eggshell. Right? So this mass of this wedge, here's your mass as a point mass, lowercase m, and here's your distance from that wedge, which is r. Okay, and that's being squared here. And then you got universal gravity constant. Okay. Now, what about the other side? Guys, if it's 3 times further away, now think about scaling. You guys remember scaling? You guys remember that big cube ahead that was all chopped up? Scaling? Right? Guys, if you're 3 times further away, how many times the surface area is this? 9 times. Right? Let's treat it as the same thickness, though. It's still 1 meter thick all the way. Right? So it would have to have 9 times the mass, wouldn't it? 9 times the mass.
But it's
right? Yeah, but it's also 3 times the distance.
square.
And that's being squared. So is there 9 on top and a 9 on the bottom? Cancels. Right. So what can you say about the gravity field inside? Gravity free interior. Right. Right. Now, what this could be helpful because are there any eggshell planets out in the galaxy? Probably not. Right. But what you can do is if you're going down inside a solid planet, like journey to the center of the Earth, and you're like digging a tunnel all the way to the center, right? Then you would say, well, what happens to the gravity field? You can say everything above you in elevation is just a series of eggshells that one by one cancels out. So you can just consider what's beneath you in elevation, like beneath your feet. Okay? Right, which I think is the next slide. Yeah, sure is. Here's the journey to the center of the planet. Right, and okay, here's this guy in a ridiculous tall tower, and here's guys running away from life. All right, so what's the gravity field as a function of distance from the center, right? And notice I'm saying with uniform density. So this is a real simplification here, because realistically it gets more dense the deeper you go because it's all packed in it, right? But or maybe it's a small asteroid, right? is it? Let's start with this guy flying away. Ah, get me out of here! So starting from the surface of the planet and getting further and further away, what does this part of the graph look like on the right side? Like at the surface of the planet, there's some gravity field. It's probably this notch right here. You guys think this point right here exists? At the surface, you've experienced some gravity field, right where my mouse cursor is. Okay. If you get really, really far away, what happens to that gravity field? Aha! Zero. Go like that, wouldn't it? Go like that. It asymptotically approach zero. So if you're really, really far away, now you experience zero gravity field from that object, right? Okay. Right. Guys, what's the gravity field right at the center? If you dig right to the center,
Zero.
it would be zero right here, wouldn't it? Because every grain of sand pulls you a different way, it all cancels out. Okay. And now this guy right here, isn't it true that everything above this guy is like a series of eggshells that cancels out? Right. So now there's just the planet beneath him that's pulling. Right. Now, if you do the math, you can show that if you're at half the radius and you're considering like a planet that size with the same density, you have half the gravity field and so on. Okay, so it ends up being a straight shot.
Slide grab.
Now, realistically, this gravity field actually increases a bit as you dig deeper, and then drops down like this because the density increases the deeper you go.
About to go in. Let's land down.
All right, you guys good? Yeah. Think about logically why that would look. All right. Ooh, tides. So, one side of the planet closer to the moon than the other side of the planet. Okay. So there are differing gravity forces on different sides of the planet and also on different sides of the moon. Yeah. A lot of moons are tidally locked to their home planets, as is Earth's moon. Right? You guys ever notice you can only ever see one side of the moon? Right. We had no idea before we set stuff up into space what the other side of the moon looked like. All right. Lagrange points. Here's another little bonus. These are points where the gravity field sort of cancels out. Now, a lot of these, it really depends on the rotational dynamics. So it's like relative to the system, like the cell 4 and cell 5. Right? Those are good places to park satellites that are or like space probes, I should say, like telescopes that look in deep space. Right. All right, I think that is a wrap on my gravitation slides. Do you guys have any questions about gravitation? All right, so I do have. Let's do. I have some FRQs popped up right here. Let's take a look at some of these questions.